One of the best thing about these deep learning models is that it can transform the very complex and noisy input EHR data to a more cleaner or more easier to visualize latent space. We also did cross-cohort validations. Basically, we trained the model on the Mimic3 dataset and evaluated on a subset of eICU, and it gives us quite good results. So I think it's pretty positive. So we are using the Mimic3 and eICU dataset to validate our algorithm. So these two datasets are very large and real-world datasets from intensive care units, and they are publicly available. So it's like a benchmark to testing different prediction algorithms.
Hello, everyone. Welcome back to another episode. Today, we have a special guest, Sihan, on the show. We're going to talk about specific AI model that Sihan developed with his team. Sihan, welcome to the show.
Yeah, hello, Rupen.
Thank you so much.
Very nice to be in the show. Yeah.
Thank you. Can you give the listeners like one liner or one paragraph about like who you are, what you do, and we can go from there.
Yeah, so hello everyone, I'm Sihan Zeng. I'm a PhD candidate at University of Washington studying biomedical informatics. And my research mainly focuses on the patient trajectory modeling and modeling of longitudinal EHR using AI methods.
So can we talk about the basics? We have lots of physicians and entrepreneurs who listen to the podcast. Let's talk about like what is survival prediction in healthcare and why it's important.
Yeah, so in healthcare, survival prediction is the task of like estimating the time to an event that's mainly like a specific event like mortality or disease recurrence or hospital discharge. And we want to predict the probability of that event over a certain period of time. And it is very important because it helps clinicians make informed decisions and personalized decisions. So for example, in ICU setting, so if we know what the patient's trajectory will look like in the future, then we can decide how to allocate those resources or whether we should give a treatment or a procedure. Yeah, so it's all about these personalized medicine. Yeah.
I completely agree with you. I think time to an event, it's something very close to my heart because I deal with it a lot. Beyond ICU, as my work as an oncologist, like we really care about time to event when we treat cancer. So for example, if we give someone a drug and then we measure the time to of the cancer progression, and we call that progression-free survival, or from giving the drug or from randomization to an event happening, event-free survival, or even like overall survival. So I think the time to event, it's like a touch base on not only like ICU, but also it's very close to my heart. And I think lots of specialties, that's what we measure. In general, most of the paper use time to event like Kaplan-Meier or survival or other types. Anyways, so what is the current state like of in general in the hospital or EMRs? Sometimes they use this algorithms to give you a survival model or something like. What is the current state of machine learning models that have been used in survival prediction?
Yeah, right. So there are many machine learning models in survival prediction. So it's a well-established area, but previous methods mainly uses like Cox proportional hazard model or like random survival forest. So these kind of models are mainly focused on the static variables and modeling the nonlinear relationship between them. And more recently, there are deep learning or machine learning models that focuses on the dynamic changing or time varying variables. For example, like a recurrent neural network, which processes the patient data at discrete times and update a latent state for survival prediction at discrete times. And also, more recently, there's a bunch of continuous time models like the neural ordinary differential equations, but they can produce these continuous time trajectories, but they are not guaranteed to make these trajectories clinically meaningful. So yeah, so that is why my TrajSurv method comes in.
Can you tell us a bit about like TrajSurv, and can we expand a bit on like longitudinal electronic medical records data and how TrajSurv fits with this.
Yeah, right. So the TrajSurv mainly focuses on two of the challenges in survival prediction. So one of them is that those longitudinal EHR is like irregularly sampled over time. So we want to accurately model the continuous clinical progression underneath that data. And the second is that we want to make the prediction more trustworthy. So we want to make the entire process more transparent from the irregularly sampled data to the survival prediction. So we designed this TrajSurv model that we mainly use a method called Neural Controlled Differential Equation, and also we added some more contrastive learning to it to make the trajectory more clinically aligned.
Can you expand a bit on that point? Like, what is you mentioned the neural controlled differential equation, and also for our listeners, the paper is going to be linked on the podcast notes. But like, can you tell me a bit more about it? Like, what is this NCDE or not neural controlled differential equation?
Yeah, right. So it's a differential equation, and it's in neural network format. So it's called neural, and it's also controlled by some input signals. So it's a neural controlled differential equation. And I want to use an analogy to explain it a little bit. So it's like a smart navigation system for patients' health journey. So, for example, ordinary differential equation or a recurrent neural network, it's like setting an initial course for a ship and letting it sail. So it evolves on its own from a starting point. But for a neural controlled differential equation, if we add controls to it, it's like a ship that is constantly adjusting its sailing course over time based on some incoming weather reports. In our case, the ship's path is the patient's a hidden health state. And the weather report is like the irregularly sampled time series measurements from the EHR. So this method can use those time series data points to continuously steer the patient's trajectory and create a more realistic and data-driven path for the patient.
Gotcha. And I think help me understand this. So right now, and I think you touched base on this in the paper, the old models like the Cox or other models, you need more like robust data, and missing data can affect the ability of the model to predict. But I don't think it was the case in TrajSurv, right? Like the data is more fluid. We can like take that EHR and if the data as is, and if there are missing data, it won't affect the model as much as it affects the old models.
Yeah, right. So, for example, for Cox model, we need to kind of impute the missing data, and we also want to transform the longitudinal data into a set of static variables or summary statistics for prediction. But in TrajSurv, it's more flexible. So it also did some kind of interpolation, but it's kind of doing it in a more intuitive way and more flexible or smooth way to construct these input continuous paths. And also it doesn't need to extract some summary variables from it. We can just input those raw data with missing values, and then they can give us a latent path. Yeah.
And also in your paper, you talk about like time-aware learning or time-aware contrastive learning. Yes, exactly. It's hard for me to spell. So what is time-aware learning in simple terms?
Yeah, right. So the time-aware contrastive learning is a special training objective we designed to make sure these latent trajectories are clinically meaningful. So we kind of contrast the latent states to some existing clinical measurements of severity. For example, there's a SOFA score in the ICU, which measures multi-organ failure conditions. So these are the ground truths of our of the patient severity, and we want to use that to guide the learning of our latent trajectory. So the contrastive learning part teaches the model to place those patients with similar SOFA scores and similar trends close together in its latent space, while pushing those with different conditions further apart. And the time-aware part is a special time mask that tells the model to be more careful when comparing patient states from very different times. So this ensures the model learns an alignment that respects the time-dependent nature of the clinical progression.
Gotcha. And so let's switch gears. We talked about the model and why it's important. So TrajSurv.
Yeah.
So what did you do to develop? You came up with the idea and then you used a couple of data sets. Can we talk about like the data sets? And my understanding is those data sets were also used to train TrajSurv. Is that right?
Yeah, right. So we are using the Mimics3 and eICU dataset to validate our algorithm. So these two datasets are very large and real-world datasets from intensive care units, and they are publicly available. So it's like a benchmark to testing different prediction algorithms. And these datasets are both from ICU, and we trained on so for each dataset we trained on one split of the dataset and test the algorithm on the other split of the data. And we also did cross-cohort validations. Basically, we trained the model on the Mimics3 dataset and evaluated on a subset of eICU, and it gives us quite good results. So yeah, so I think it's pretty positive. Yeah, and the data we're using includes 53 most commonly used clinical features. For example, the lab results and vital signs and demographics. And we use the data collected over the first 36 hours of their hospital admission to predict their survival in that admission.
Gotcha. And you mentioned the TrajSurv performed well. Like, how does this compare to old models?
Yeah, right. So we are using 3 different metrics to evaluate TrajSurv. So these are common survival prediction metrics like the C index, Brier score, and dynamic area under curve. So for example, on Mimics3, our TrajSurv C index is around 0.80, and other deep learning or conventional machine learning models are around 0.75. Yeah, so it's like a pretty large margin, but and also the cross-cohort validation, our method can give the C index of 0.76, which is also quite impressive. But I want to highlight that these performance differences is not the main contribution of this method. I think the most exciting part of this work is the interpretation of the TrajSurv model, which I think it's very interesting. It's like a digital representation of the patient journey. So yeah, so I'm very proud of that part.
Yeah, I completely agree with you. I think I can also share the table here for people who are, I think this is the table that we're talking about. And you mentioned TrajSurv, the area under the curve is 0.8. So in simple terms, this is get area under the curve, which covers the specificity and sensitivity. Usually 0.7 is borderline, not that helpful. 0.8, 0.9 is great. 100% is like very good test, but that doesn't exist in real life. So 0.8 is very reliable, and this is the TrajSurv when compared to the other models. Okay, so we talked about the data and how we try to, or how did you, I would say, train TrajSurv. What do you see, or where do you see the future implementation of TrajSurv in the workflow of a physician or in the hospital, or even embedded within DMR?
Yeah, right. So I think TrajSurv in the future can be a clinical decision support tool rather than a replacement of the clinical judgment. But currently, it's still in its young age, and
Early,
we're
yeah.
kind of very young age, and we kind of wanna show people that these latent trajectory can be a visualized tool for people to see what are the patients look like over time and what are the clinical progression over time. So, for example, a clinician can visualize a patient's trajectory over time on their screen and see if if the latent trajectory goes from a region that is more like a milder symptom to a region with more severe symptom, then it might trigger some warning signals that this patient may need more intensive care or some more interventions on it. Yeah, but and also the interpretation of these methods can make it more trustworthy for the clinicians, and also could highlight those important features that drives the changes of the latent trajectory.
I just want to add a couple of points there. I think what the problem with, or I wouldn't say the problem, the limitation with physicians' ability to predict survival or predict decompensation of a patient is limited by several things. One of them is the time constraint and ability to visualize data and multiple important points of data at a specific time. Let me explain more on that. If I'm on the ICU rounding and I see a patient the nurse comes to me and she's like worried, oh, like the heart rate is like 110, the blood pressure is like softish, like it's around like 100. I might go back with the data, like I would look at the trend of the heart rate and the blood pressure over like a couple of weeks, and I see that that might be like within the patient's range or something. But I usually, especially given you are working in the hospital, the constraint of the times, I can't see, or I might not look at the heart rate and the blood pressure in addition to the white blood cell count, in addition to lactate, in addition to other markers over 4 weeks, 5 weeks. And I think that's what lacks from the ability of the human eyes and to visualize multiple points of data over a longer period of time. And that's where the machine comes in to help us to visualize that trajectory. And my take home point, and please correct me if I'm wrong, TrajSurv can combine different patients to different categories and tell you, well, according to this patient belongs to this category, although something like this might not exist in the literature and the guideline might not have specific score or a cutoff, but TrajSurv is able to group those patients and tell you, depending on the white blood cell, heart rate, lactate, and other markers, this is the trajectory of the patient that we are most likely going. So you should transfer him to more intensive monitoring area, or the patient is improving. Is that right?
Yeah, that's right. So one of the best thing about these deep learning models is that it can like transform the very complex and noisy input EHR data to a more cleaner or more easier to visualize latent space, so that we can observe what are the latent states and latent trajectories look like. And also TrajSurv is able to cluster those latent trajectories into some clinically meaningful patterns. And just as you just said, we can, by doing this categorization, we can see how a patient goes on and what kind of interventions can we do to that patient.
Yeah, I can share, I think, from your paper that this is the figure, I think, that tells the story. Is that right?
Yeah, right.
Yeah, so here, as we can see, so this is the figure that you can go ahead, Sihan, and talk about this figure and explain to the people who are watching the YouTube video what they are seeing here.
Oh, yeah, right. So the figure 3 is the interpretation for the feature to trajectory interpretation, and we're using a vector field interpretation on this, and the figure 3a shows the columns of that vector field, and we can use the length of those columns as some kind of feature importance, and the cosine similarity between those columns as a feature relevance between those features. And figure 3b and c shows the top important features in the ICU setting, and also the relevance between those features. And we can see that it's pretty aligned with the clinical knowledge. And figure 4 is the interpretation from the trajectory to the survival outcome. And we're using a latent trajectory clustering to do this interpretation, and we clustered it into 4 subgroups. And we can see that these 4 subgroups have different average latent trajectory in different colors. And they also correspond to different clinical progression patterns and different survival outcomes. For example, in figure 4b, we can see the yellow cluster. So these patients in the yellow cluster, they initially have a very severe condition by a high SOFA score, and over time they improve very quickly over time, and after 36 hours they become pretty good after this period of time. And we can see that their survival after 36 hours is very good, visualized in figure 4c. And it's actually the best, associated with the best survival outcome. Yeah, and also the green cluster is with the most severe condition, and they keep doing bad. Yeah, and they have a very bad survival outcome. Yeah, so using this visualization and clustering, I think it can show that TrajSurv can identify these clinically meaningful patterns.
Yeah, also like I want to summarize this for the physicians who are watching is like if I'm rounding on an ICU and I have like 20 beds, we can start we start from this point, and then TrajSurv is going to categorize these 20 beds into different categories, and depending on their blood work abnormalities and other type of data, it will tell me which direction is the patient is going. So this is also in simple terms. Of course, this is like Sihan said, we're not replacing the physician's judgment because there's part of the clinical experience where AI doesn't really, or AI doesn't have that acute or well accurate clinical judgment, and sometimes what you see is different what the numbers say. But this could help us to identify which patients can be sent outside of the ICU safely to the medicine ward to be monitored versus which patient need to stay here longer for the monitoring because they are more likely to decompensate. One of the things that we face, especially if you're running an ICU, is like you send a patient from the ICU to the medicine ward, less severe acuity bed, and then they decompensate, they come back later. So this can help us also in patient allocation in the hospital.
Yeah.
All right. And I think we talked about latent trajectory and we talked about this. So what's next for you? After this, like, are you trying to explore similar survival models or in oncology or other spaces, or there are like other steps to improve TrajSurv?
Yeah, right. Yeah, so I think there's a few exciting directions for us. So, for example, from the methodology perspective, I think the TrajSurv currently requires a severity score like the SOFA score to supervise its training and make the latent trajectory more clinically relevant. And I think this part is a little bit rigid right now, and in the future we can make it more flexible using like some existing important features rather than these kind of well established score to train the model. And also currently the latent trajectory of TrajSurv is only developed based on the lab results and vital signs. And I think a very interesting future direction is that we want to add some interventions to this trajectory and see how it moves over time. And if we, for example, if a patient has certain trajectory, like in the first 2 or 3 years in their cancer after their cancer diagnosis. Here's a time for selecting the right treatment for this cancer patient, and we want to compare different treatment options. So we can add those treatment options to the TrajSurv model and see how the latent trajectory goes over time if we select this treatment. And we want to so that we can choose the best treatment option. So it's something like a counterfactual prediction stuff. So I think that's an interesting thing to do, to visualize this counterfactual prediction. Yeah, and also I think TrajSurv paper is based on the publicly available ICU dataset, but we can definitely expand it to other domains like oncology and also other different diseases.
Awesome, great. Sihan, thank you so much. I really appreciate you being here. Again, for the listeners, the paper, we're going to mention the archives link in the comments below. Feel free to check it out and read it. Thank you so much, Sihan.
Thank you. Thank you, Ruben.